Ladies and gentlemen, we spent so far this year 6, 8 months almost learning design, learning visualization, learning spatial relations. Now, none of you ever questioned it because all of you have God-given talents. Most of you sketch your work. And you do vanishing point perspective, which means you're drawing accurate, real-life perspective with diminishing scale as we go into the background. You do it naturally. You do it in your sketches all day long. You don't even question it. The problem with that is when you go out to the real world and you get a job, someone's going to ask you to have specifications. If you're a graphic artist, an interior designer, or a showcase designer at a museum, gallery designer, somebody's going to ask you for specifications. Somebody's going to ask you for real-world dimensions in order to create the exhibit. You can't give them a sketch. This is the exact opposite. This is the bizarro world for us. Because the sketch that I tell you is worth 1,000 words and talk is cheap, now is the opposite. The picture means nothing because things are different sizes in true perspective. So they are no good to us. So we need to learn how to do something. And ladies and gentlemen, I am very careful when I say this. Please do not jump up out of your chairs. We are going to learn some math today. Okay. It's okay. I'm here for you guys. But math, and you know how I feel about math, that's why I became an artist, is difficult for somebody like me because I don't see numbers like I see pictures. I'm dyslexic, I have reversal issues, and to me it's this black and white scribble on a page. They don't mean anything to me, but they do mean something to a lot of people. We have different types of learners. We have learners that are non-visual. We have learners that have to read step by step, simple, one at a time instruction to understand. Most of us aren't that person, but it does exist. So we're going to dabble into that arena for a little bit. Interestingly enough, it is on your task list. The task list that we always talk about. This is critical. We are going to talk about some Pennsylvania standards that involve math in a way that will help you in the real world. It's this term. You've all heard it, you all know. As soon as I say it, you're going to be like, yeah. Geometry. Geometry is our visual language of mathematics. I actually love geometry. When I got to, say, 8th grade and had my first geometry class, I loved it. It was shapes. It was visual. It was understandable to me. Fortunately, I can teach you through geometry this lesson. We're going to use a technique and a formula called the Cartesian plane. The Cartesian plane is a formula that measures the x and the y axis from its origin to describe the size of a shape. We're going to talk about that now. First, I want to ask you, since we started talking, why do you think you would ever need to put numeracy, which would be numbers or dimensions, on work that you've done? In the real world, forget class. Who would want to see numbers and why?
3D printing.
Elaborate. It's a good answer, though. Hey, think about it. When we talk about 3D printing, we are talking about dimension. We are talking about an x and a y axis and an origin. Now, that's mathematics. A lot of that is predetermined in our software. Thank God. So, you're not wrong. We're not going to do a lot of math. We aren't for 3D printing. Think about the real world when you have to communicate with another individual. I don't want to say the opposition, that's the wrong word, but people you work with. Don't forget, as graphic artists, you're going to have to team up with people who are actually physically doing the work. Installation specialists, construction workers, architects, interior designers. Even as graphic artists, you will work in spaces. Your signage, your infographics have to be hung and displayed. So, one more time. Let's see if I can get another answer. What do you think, Patty?
If you're designing like a product for a house or something, whoever is actually making the product needs to know how big the product is.
Absolutely. It's pretty straightforward. It is pretty straightforward. Anytime you're designing a product or a service, it's going to require physical dimensions that have to be tangible, written down, so the product can be produced or the service can be executed. Now, going a little bit deeper into that, for us, everything is about perspective. Even if it's 2D graphic, it has perspective in the imagery. So we still have to understand it. There's two terms up on the board. We have what we call vanishing point perspective, which I know you've heard a million times and you do all day long. But we also have this term axonometric perspective. Does anybody know anything about either one of those that they could share before I elaborate? Gerald, what do you think?
The vanishing point perspective, wasn't that the one that's like supposed to be 3 dimensions? Like it starts with the back and it kind of comes out to a point almost.
I think you're saying it all correct, just a little, your ordering's a little incorrect. It's okay though, but yes. Vanishing point does start with a point in space. Everything works from that point, the vanishing point. Yes, Maddie?
I'm not sure, but axonometric probably means it works with some axis.
Very good answer. That's even deeper than I thought into it myself, thinking about it. I know what it is, so I don't read as deep into it as you, so I appreciate that. You're right, though. Axonometric, so we're going to skip back and forth a little bit. So we've got Gerald and Maddie here. Axonometric is literally about axis. The axis is all angles are perpendicular. You can pick that angle. A lot of drawings are done on a 35-degree angle or a 45-degree angle, but that sets the axis. But there's something that is very different between vanishing point perspective and axonometric. Now, Gerald mentioned it. Vanishing point, 3D, starting from a point in space. So if I were to begin a vanishing point perspective, I'm going to start with a dot in space. Now, you also sometimes set this when you begin this drawing, and I'll help you understand it by drawing this on it.
Horizon.
There we go. A horizon line. Very good. Thank you. Horizon line. All right. Really simple because we have a visual lesson also. Here's our starting point. There's our cube in space. What this means is that every angle, now this one's going to be tough because look, the angles are very extreme. But you'll notice that if we now connect and complete this box, it diminishes in scale as it moves through space. Tell me why that's a problem in specifications. Why is this dimension, this is a cube by the way, a perfect cube. This dimension is 2 inches. This dimension at the rear of the cube is now 1 inch. Wait a second. What's the problem?
Without writing, without like writing how big it is, you won't be able to know because it gets smaller as it goes away, or it's further away.
Yes, 100%. Vanishing point perspective is true. It is real. It is how we see things in the real world. We always joke around about looking to the cafeteria. Everybody's an inch tall when you look down the hallway because of a vanishing point. Now, if I sent Maddie to the cafeteria, she'd be an inch tall. She didn't shrink. She didn't go through a time machine. She vanished in perspective, in space. So you cannot use vanishing point perspective in real world drawing, real world specifications. Remember that word, specifications. 2 inches and 1 inch means it's not a cube. It means it's a trapezoid. It's not right. So the layman being the worker, the installer, the co-worker, whoever's helping you is going to design and build the installation incorrectly. Imagine if we took a photograph, an N.C. Escher photograph. We all know N.C. Escher's crazy work, right? Vanishing point perspective, and built this space in reality. What would happen if you walked into the room? Ariel, I see you thinking. What do you think what's going to happen? You walk into an N.C. Escher room. Everybody saw Willy Wonka's Chocolate Factory, right? The original. You remember the scene where they're walking down the hallway and all of a sudden they're like having to duck and they're shrinking and the walls are closing in? That's what they mimicked in that scene. They actually really shrunk the room down to create true vanishing point perspective. But by the time they walked to the back of the room, everybody was huddled down in a ball and the door was 2 inches tall. That's what would happen. Now, in order to create true dimension so we can provide real specifications, we're going to switch our mentality and not use a vanishing point, but use an axis, as Maddie said. So when we draw a cube in axonometric space, we're going to pick an angle. We're going to pick a 45 degree. I just wrote 40. That's how dyslexic and messed up my numeracy is. So 45 degrees, which means from that point, every angle stays 45 degrees from the start, from the origin. They do not vanish because now we can connect the shape, even if it's a little off. We have a perfect cube. Now, I know I didn't draw a perfect cube, so I'm drawing it sideways for you guys to see. But 2 inches is 2 inches is 2 inches is 2 inches. You can actually record these dimensions and specifications right on the drawing, and they won't look wrong. They will look right, they will be accurate, and effective. I can tell you this. You're looking at a drawing in vanishing point perspective of electrical outlets on a wall. By the time you get to the 10th outlet, how big do you think that outlet is? Right? It's about 1/4 of an inch long. So it's going to mess up an installer. A trade-educated electrician has gone through schooling, at least 2 years of schooling in trade, maybe further education. They become a master electrician. They're sophisticated individuals. But they're not going to want to see a vanishing point perspective. It's not going to make any sense. They're not educated in that. They're educated in reading mechanical drawings, which are done in axonometric perspective. Okay. Now, here ended the introduction to math, to geometry, and understanding axonometric vanishing point perspective. We're now going to move on to our visual lesson and our actual project for today. Cool? All right. Thank you, ladies and gentlemen, as we turn our attention to the back of the room. As you know, we do theory and written in the front, and we're going to do video instruction in the back. I love learning on the blackboard. I love drawing. I like getting perspective and drawing things up there, having you guys come up and do that. But we all feel more comfortable seeing pictures. So we're now going to go into a visual lesson on the Cartesian plane. Putting it into perspective is basically what we're doing. Can anybody tell me where these images came from? Yes, the Philadelphia Art Museum. This was pretend with me that the art museum has contacted you and has asked you for a specifications sheet requiring the dimensional layout of your next art exhibit. That's what you're going to do. You need to put dimensions on paper. You can't send them a sketch because it doesn't tell them the math. So here we go. Moving into math visually. There it is. Rocky's missing. We can all jump up and down and do that later. But that's the art museum. This is the Great Hall. I thought let's use the Great Hall to hang our artwork, but it's a bit too great. But let's feel it. Let's get into this. All about perspective. Here's our different perspectives. This is vanishing point visually, done more accurately than I did on the board. You should recognize this lower left drawing. That is the perspective grid in Illustrator. Very complicated, but it is showing vanishing point. It is also showing that they're using it as a 2-point perspective, but you can see the grid. The grid's nice because it also tells you dimensions. So a lot of this work, you don't even realize you've done it because the computer does it for you. But we're going to do it mechanically, by hand. And we're going to use the method that you see on the right. If you look at this picture of the illustration on the right, this is a layout of telephone poles. They have to be laid out equidistantly down a road. Now, if we look down that vanishing point perspective, each telephone pole gets smaller, and the distance between gets smaller also. So you can't do the math on that unless you use the rules of the Cartesian plane. Now, before we move on to the Cartesian plane, we're going to talk about that axonometric one more time. I've got good pictures I can show you. Look at the different perspectives. Vanishing point, hard to see it because it's a small cube, but look at that axonometric. It is all perpendicular angles. No angles run into each other or vanish in space. These types of drawings are used for accuracy in dimension and for mechanical drawing. All right, Maddie mentioned this earlier, but look at this picture of this engine, this motor. There's nothing on this motor that's, well, I shouldn't say nothing, but look at all the dimensions. There's round shapes and angular shapes. So someone's got to come up with the map, the specifications, the dimensions for this drawing. If it was done with vanishing point perspective, the front bracket will be a different size than the rear bracket. So, if we now make all of our angles of perspective on an axis the same, what can we do with a ruler? Not our hands, with an actual ruler. Emma, what do you think? Right, you can measure because they're the same size. So you can visually measure your dimensions. An architectural blueprint of a home is done in axonometric perspective. 1/8 inch equals 1 foot. We use what's called a scale because you can't draw a house at full size. You can now physically walk all over that drawing. This window, if it's a standard window, is the same size as that window, that window, that window, that window, and every other window in the home. And they can be measured with, like Emma said, a ruler. Delicate, guys. We're going into this. Okay. Believe it or not, there is a standard for the state of Pennsylvania educational system requiring you to understand and analyze relationships between two-dimensional and three-dimensional objects. That is a PA educational standard, one of which is on our task list to be taught within our curriculum. I was scared. I had to sit down. I had to get my dog and lay there in comfort until I got into this lesson. And then I realized what we were talking about. Talking about geometry, we're talking about spatial relations. This is what we do all day. We're just now putting it on paper and coming up with numeric answers for our real dimensions. All right. What is the Cartesian plane? Does anybody know this? Has anybody had this? Don't forget, guys, you have geometry. You have math. You have algebra. You have trigonometry. Think about the connections to your life and then the real world. Has anybody ever seen anything like this in geometry class? What do you think, Michael? Does this look familiar?
A grid?
It is a grid. Yes. That grid has something very specific on it. Something that we talk about in Illustrator all the time. The X and Y axis. Right. We have to have a vertical Y axis and horizontal X axis and then an origin. Everything has to start from somewhere. Your object has to be, nothing floats. It has to sit somewhere. So this formula is a grid evenly spaced out with a Y vertical axis and an X horizontal axis that meet at the origin. This allows us to measure two-dimensional shapes. I found this online. What a neat little exercise, laying telephone poles out. Now, hopefully none of you guys ever are laying telephone poles out as graphic artists. Because if you are, something went wrong. But you might be asked to do the specifications for it if you further yourself into a field, say, of engineering, interior design. You could. You can jump out of graphic arts and continue on your education and do that. And you'll think back and say, Mr. Anderson taught this in graphic arts class, and now look at me, making architectural drawings. If you were laying out telephone poles with a vanishing point, not an axonometric, how are you going to know the distance for, don't forget, we work in reverse. You can work forward, but we're working in reverse here. So say we set the first pole in place. We know with the Cartesian plane, there's an X and a Y and an origin. So we can set our second pole. But how do we know how to place our third pole? That is the million-dollar question. From those two pictures, can you see how this is building? Does anybody have a hint to the answer to that question? The hint starts with an M. Close. Not measure. If you're looking at a person, their belt is at what area of their body? And that's in what area of, yeah, the midpoint. If you know the midpoint of an object, it can help you determine width in space. So now that we have two telephone poles in formation, we create a rectangle. You can crisscross upper left to lower right, upper right to lower left, the contact points of the X and Y origins, and it tells you the midpoint. Once you know that crisscross midpoint, you can draw it in and have that layout. I felt this was like inspiring when I saw it. What happened here to create the position of that third pole?
Second.
The second pole helped us find the midpoint.
Yeah.
But it's a tricky question because it was drawn,
Yeah.
but not necessarily shown in steps.
In that first picture, the second pole's in the middle, so like the other two are evenly spaced.
This is true. Do you now see an angular dimension or an angular notification that helped determine that? Look at the angles. In the first drawing, the angles between upper and lower midpoints were on the first and second pole. Now look at those angles. Where are they now?
Yeah, the second pole's in the middle. They're in the first and third.
Right. So what happened was, because they knew the midpoint,
Yeah.
if you go to the top right, go through the midpoint of the second pole, and continue that line down, it intersects with the origin, the starting point of the third pole, and so on and so on and so on. That's how you go back in space. That guarantees you perfect layout in vanishing point perspective. Pretty neat. Now, cool picture. I masked it out for you and made you a white wall. What we're going to do is pretend that we've been contacted by the art museum to create an installation. Whoever this artist was fired, or someone stole their artwork. I don't know. Whatever. But you're now on exhibit. So you have to send a specification sheet to the Philadelphia Art Museum determining the size of your art and the dimensions of it in vanishing point perspective. They know the actual artwork size. They're holding it. Say it's a 2 foot by 2 foot square. They know that. What they need to know is the distance between the pictures. And they can't determine that. You have to determine that. So we're going to use this grid, this Cartesian rule, to map it out. We're going to do it the way we do it, artistically. We're going to have fun. We're going to draw it in 3 dimensions. You're going to watch the video provided showing me doing the exercise. So you have a guide. You also have option 2 room, in case you don't like the other one, in case your rooms that you pick are different color and you wanted something different. I try to give you some variety here. I don't want you to take 1, 2, 3, 4, 5, 6, 7 different pieces of art. That's not the point of this. The point is to pick one of your art pieces. Create the gallery wall. You can alternate the height of the shape or installation area once you determine the midpoint. Here's the included video showing what happens as you lay out the Cartesian grid on the file. I'm giving you a transparent grid, black rectangle with the midpoint already laid out. The video shows you how to do it. We are going to walk through it one time so you can see. After you lay this out and you can see those objects in space, you can physically go in and measure the distances by placing guides in Photoshop. We have knowns. We've talked about them all year. Use your rulers. Know the dimensions of your file. It's a 24-inch file. We're going to call that our scale. That's our known dimensions. So if you measure that with the 24-inch scale provided, that might be 2 inches. I'm not saying the answer because that's what you're going to determine. 1 through 7 are the instructions of what that needs to be done on the assignment. Please read through them carefully. We will go over them as we progress through the lesson. Here is your specifications sheet. All you're doing is starting from the foreground, recording the original size of the image. Once you lay them out using the Cartesian grid, you will then record the size of the middle image, mid-ground image, and then the background image. 3 pieces required. You can do more. That's on you. As always, our workflow chart. So you are tracking and making sure you're following this assignment accurately. We are working with task 508, which is under Duty 500 digital imaging. This is an intermediate level function of using Photoshop, a raster image program. We're using math. All right. And last but not least, your checkpoint. Check it off as you go so you know you're not missing any details. There you go, guys. That's our lesson. We are now going to review the video, hands-on. We're going to watch it done, and then we're going to go back to our seats and perform the exercise. Thank you very much.
Gentlemen, welcome to our demonstration of the Cartesian plane. As you know, as artists, we all work in 3 dimensions. We all use vanishing point perspective every day in our sketchings, our renderings, and our designs. But if somebody were to ask you how to mathematically equate the dimensions in your work, how can you provide them with the information? Well, we're going to do a little bit of geometry, and we're going to fill out what is known as a specifications sheet. The specifications sheet is what you provide to your installer. Our installer in this case is going to be a worker in the Philadelphia Art Museum. This is one of the gallery hallways in the Realism Hall. And I've eliminated the gallery for you guys specifically and created a blank wall. So per our lesson, you are going to get yourself a selection of artwork. I'm going to take this lovely picture of my wife, and I'm going to bring her into one of the 2 museum rooms provided for the lesson. I am going to use the green room. I'm going to paste this layer in, and I'm going to now scale the room to a basic set of dimensions. We know that we use distort to create the vanishing point of our room. We foreshorten and we begin to place our artwork in a room. We don't know the original starting dimensions until we get it in place. Now, it's huge if we slide it down the wall, but as we bring it to the foreground, we'll notice that it is not that large. I'm going to actually increase the scale quite a bit so that you can see how this room is going to look. I'm going to change that, and I am going to do that again because that did not look appropriate. There we go. I'm scaling it more. I like this angle better. I don't like that. I need to be careful in the ways in which, there, look how nice and smooth. We want to watch the way we scale these images. Look how quickly we lose perspective. Don't forget, we need to follow the Cartesian plane. So let's pretend that is section 1. For the lesson, I also provided the Cartesian grid as we see here. It is a basic X and Y axis, which has a midsection created by the cross of the upper left to lower right coordinates. This is the basis for the Cartesian plane formula. Going back to our room, let's activate a layer for this Cartesian plane. You'll see. Now, to do it successfully, I'm going to make a copy of this layer and hide it for later in case I want to use it for something else. I'm going to distort this layer to the size of the beginning or the background of the wall. I'm going to shrink it down to the height. Look at the height of the ceiling and the floor. You have now set the precedent for the height, which is the vertical dimension, which if you look at your Google slide, you can always refer back. You can go through this lesson and you can look at all of the different pieces of information that show you X and Y axis, So we're using vocabulary and terminology that make sense. The Y is the vertical, the X is the horizontal. We are now going to distort this by holding Shift and creating our first gap. Now look at this on the wall. It is perfect here. But is it perfect here? No. We are going to put it in position. We are going to zoom out a little bit so we have plenty of room to manipulate these lines. I'm going to stretch the proportion to the edge of the room, and then I'm going to then readjust these angles to match the floor and the ceiling lines. Now all that's done is give us a center line. And we know that the center line is critical in understanding the Cartesian plane. So now that I have a center line in my room, I'm going to actually create a new layer, and I'm going to draw that in, and I'm going to do it in a very bright color. I'm going to get myself a super bright yellow, and I am now going to create this line, Shift off the page, and I'm going to increase my stroke a bit, and now I have my midpoint. So now I have the beginning of organizing the distance for my next images that move backwards to the vanishing point. But we're going to create even symmetry by using the Cartesian plane. The first thing we're going to do is we're going to draw the vertical. And you can see these two verticals. Now, we have defined the Cartesian plane by understanding, and we can't see it because we're going off the page, that we go from the top right of the y-axis to the midpoint of the secondary vertical line of an image. So if I were to follow this line in space, click and pull, we're going to cross this midpoint, and it's going to take us to the floor. We're going to deselect, and we're going to see that where it intersects with the floor is evenly spaced distance from artwork to artwork. We're going to draw a new vertical line from this point, and we're going to see there is our secondary line. So if we go to our artwork and we copy and we paste, we know we have to now distort. The easy thing is we shrink it first. But it doesn't start until here, because we want an even amount of spacing between pictures that match the width of the main art. Now, if you have Snap-on, nothing's going to work. Line it up. You should not have to change too much of the vanishing point, maybe just a touch. Now, when I look at this, the assignment requires 3 to 4 pieces. Now, if you put your picture in the room as big as I have, you'll notice you can only fit 2. So you would either have to redo it or start over with a smaller section of rooms. How do we do that, you say? Well, if we hold Shift and activate all of our layers, and we do Command T, we can reduce them. Whoops, sorry, I am missing a room. I did not. Merge. Well, you know what? They're smart objects, so we're not going to be able to do it that way. I can cheat. Let's do these 3 layer. If you notice this, they're smart objects. Rasterize layers. That way you can combine and transform at the same time in unison. So I will shrink. Look, there goes everything. My wall, my Cartesian plane, everything. But you'll notice it is distorted because we're changing the overall scale. So we're going to have to readjust our Cartesian plane. And we can do that. We just want to make sure that our vanishing point don't forget, we can turn all these off when we're done. But these are the walls in perspective. These are long pieces of art. But now, following the method of the Cartesian plane, we can now zoom in and add another vertical row because we have the 3rd dimension. So we are going to take and create a new vertical. Let's do it on our top layer. We're going to bring that up. We now have a vertical for the y-axis. We can now go from the upper right to the midpoint and go across, and that is going to cross this dimension here. So look, you can add to this grid. Don't forget, it's just a grid. We're going to eliminate it when we're done. Click and shift. There's the base. Click and shift. Here's the top. So as we go, you'll notice less and less space for your images. Let's do the vertical. Theoretically, we'll click on our image. We will Command J. We will bring it down to this place. We will change the scale. We will reduce it to fit within. There you go. That is the 3rd picture, spaced evenly within the grid. You can now turn the grid off because it starts to get confusing. You can look at all 3 of your images in space. You can move them succinctly. They are now evenly spaced on the wall. There is no lighting. There is no effect. So if you compare it to the left side where you can see the shadows and the lighting, yes, it looks different. This does not look real. I can really quickly, these images, let's get them all on the same plane. There we go. Pictures, pictures. Do some quick lighting because I know what you guys are thinking. Mr. Anderson, they don't look real. Let's shadow them real quick. Hide, levels. Let's give them a little bit of life. This is what you guys are going to do too. You're going to go to your base layer. We're going to light it a little bit. There. Now the shadows are there. We're going to put a nice overall glow on the wall, because I know how you guys think. Now we're starting to see some reality. Okay? We can tweak all day long. The exercise is on perfect geometry, guys, not perspective, and creating the proper illusion of light and dark. What's odd about perspective, the reality of this is these lines all start to look like they're not perpendicular, but they are. If I were to connect from this tip to this tip, you'll notice that they all line up. Let's get rid of that one and move forward. Now, the key is to now measure the distance from the original to the mid to the background. So foreground, midground, background. You're going to record this information on your specifications sheet in your Google slide. So I'm going to go back to Photoshop because you're wondering now, how do I come up with these dimensions? Very simple in Photoshop. Our file is predetermined to 24 inches. We are going to use that as our reality. For this exercise, I'm not going to be giving you a scale that says a 1/4 inch equals a foot or an 1/8 inch equals a yard. We are just trying to learn and understand how to equally place objects on a vanishing point perspective plane using the Cartesian plane so we can provide some specifications. Theoretically, if it is a 10 by 10 box and they're evenly spaced, there's 10 feet in between, 10 feet for the next picture, 10 feet in between, 10 feet for the next picture. That would be the specifications. But I want you to tell me what they are in the vanishing point. So what you're going to do is you're going to measure the width of each picture and record that information. And you do that by making a marquee from left to right. Because marquees can have dimensions. So we're going to look at that dimension and we're going to measure using guides and our rulers, and we're going to realize here 19 to 22 inches. So that is 3 inches wide. The vertical is not tangible because it's different on both sides. So you're going to have to start at the origin, which is is the place closest to you. So the origin for us on this picture would be the right side, top and bottom. Those dimensions, if we use our grid, are 8 1/4. So we're 3 by 8 1/4. So go back to your Google slide, foreground. X and Y. 3 by 8.5 inches. Let's make sure we put inches here. Then we go back to the next exercise. We're going to now grid this. We don't even need to put a marquee. We can just grid it out. We can even use the grids from the last image. We are now exactly 2 inches wide by 4 inches tall. So you are 2 inches wide by 4 inches tall. And moving on, doing our third. In place, move over to that vanishing point, move over to here. And now we are, let's zero out our guides, 1 inch by 2 inches. So 1 inch by 2 inches. Now look at the math, guys. 3, 2, 1, 8, 4, 2. Now the 0.5, we are in Photoshop and we are doing it through perspective. I guesstimated a little bit. This is a guesstimation process because we are using vanishing point. If we were laying this out in an axonometric, which we've talked about, the axonometric is perfection, we would be making sure this was precise. Interesting that the exercise asks you to space these images evenly across a plane. Well, your answers should show that. 3, 2, 1, 8, 4, 2. They are equidistant numbers, thus proving that you have successfully created this image. And on top of it, you now have a gallery wall piece of artwork that you could create to submit for your portfolio. Please save your file, print for critique. Please add any additional information you'd like to the artwork to spruce it up. Fill out your specifications form according to the lesson and hand it in. Thank you very much, guys. Have a great day.